Hello everyone, welcome to all of you in my lecture today. In my previous lecture of heat transfer, already I've discussed about the definition of condensation and I have derived the velocity profile for the condensate layer on the vertical plate. Okay, so here in this lecture, I'm going to derive about the heat transfer coefficient and this boundary layer thickness that already I've discussed about the significance of this boundary layer for the condensation. So this is the boundary layer. And I will be deriving the formula for the boundary layer thickness, that is delta, and heat transfer coefficient for this particular problem. So let's try to understand. So already we have derived the velocity profile, that is uy, that is rho l minus rho v, where rho l is density of liquid and rho v is density of vapor. This is acceleration due to gravity, and delta is the thickness, and y is the length scale in the vertical direction, right? So here I'm going to discuss about the mass flow rate for condensate, right? So let's try to understand. So our when we talk about the condensate layer, so it was like that. Okay, so the cross sectional view of this condensate layer was like that, right? So let's try to understand. Uh, so yeah, so this length was delta minus y. This length was dx, and this length was w. So, since the velocity profile of the condensate layer is like that, so the velocity profile was like that. Okay, it was a parabolic velocity profile. Okay, it was a parabolic velocity profile, and that you can see from the mathematical expression of the velocity is also there in the previous slide, right? So you'll have to calculate the mass flow rate. So generally what we do in the mass flow rate, m dot, that will be equals to that rho and uy into dA. So dA will be what? That is W, that is cross sectional area we used to take for the calculation of mass flow. So this area will be taken, right? That will be our dA. So that our dA, that is equals to W dx, and U as a function of y, that already we have derived, that is equals to rho L minus rho B upon mu L into Z, and del y minus y square upon 2. That is a parabolic velocity profile, okay, that you can see from this particular formulas. And here, that is rho is actually we are interested in calculating the mass flow rate of that liquid condensate. So here this will be equals to rho L. So can I substitute the value here? That is rho L, velocity of value of u y is uh, rho L minus rho v upon mu L. Mu L is the viscosity of the liquid condensate, right? So G into del y minus y square upon 2, and that is W, and that is dx, right? So and that is equals to 0 to delta. Okay, so sorry, so here the cross sectional area will be that is, I will be taking like that. So cross sectional area will be like that. So it will be at a dy distance from y, and the thickness inside this plate will be w, right? So that will be w dy. Sorry for that. That is w dy. Again, I am writing here. I hope it's clear to all of you why I am taking w dy, because again I am letting you to understand. Since I am going at a distance y from the wall, right, having a thickness of dy, right, and this is the width of this plate. So this is dy and this is w. So The flow will be like that, right? So that's why I'm taking W dy as a cross-sectional area. And this y will vary from 0 to delta. Why? Because this distance is delta. So we'll have to calculate the mass flow rate throughout the whole delta, right? So can I take all these part is common? So it will come outside of the integral. So rho L minus rho B upon mu L into G. And now that del Y minus Y square by 2, it is a function of Y. So that's why it will be in under integral 0 to delta. And here we'll have to multiply by W as well, right? So next, it's only a mathematics now. So now we can write m dot that is equals to rho L, rho L minus rho V upon mu L GW and del Y minus Y square by 2 dy 0 to delta. So that is equals to rho L minus rho V upon mu L GW and that is equals to del Y square upon 2 minus Y cube by 6 and that will be 0 to delta. So that will equals to rho L minus rho V by mu L GW and when we substitute delta, so delta Q by 3, sorry, delta Q by 3 minus delta Q by 6. So that will equals to rho L minus rho B upon mu L GW. So that is equals to 2 delta Q by 6. So 1 by 3. So it will be equals to delta Q by 3. So our mass flow rate we will be getting that is equals to rho L minus rho B upon mu L GW and delta Q by 3. That's very important correlation. Sometimes uh, you'll get the question from here that everything will be given in the problem that is rho L, rho B, G and the width of the plate. If someone is assuming that width of the plate is W is equals to 1, so you can calculate the mass flow rate, or if mass flow rate is given, then we can calculate that boundary layer thickness for that condensate layer that is delta, right? So now next thing is that rate of here you can see since uh, this condensate layer, this was the thickness that is dx, right? And here that is delta minus y, and here inside the plate that length was w, right? So we can calculate dm dot by dx, right? So that is equals to rho l minus rho v upon mu l gw, and that is equals to del square d del by dx, right? So you can also calculate mass flow rate, variations of mass flow rate with respect to the vertical direction, right? Since because here the condensate layer is like that, the velocity profile is like that. So it was our y direction and it is x direction. So at a particular length of the plate, because if the total length we have assumed is L, so here the length of this plate was L. So we can calculate the variation that is dm dot by dx also. It's a very important parameter. Now, just try to understand one important concept over here that I am letting you to understand. So since, right, so try to understand one thing. Since here I am assuming this is dx, right? So mass flow rate at this particular location is m at x, and here mass flow rate at this particular location is m at x plus dx. So we can do the Taylor series expansion here. So m dot x plus dx. So we can write m dot at x minus m dot at x plus dx plus q dot by lambda that is equals to 0. Why? Because q dot mass flow rate, sorry, heat transfer rate that is equals to m dot into lambda. So can I write m dot that is equals to q dot by lambda, right? So m dot x, right? We can write m dot at x minus m dot at x minus dm dot by dx into dx plus q dot by lambda that is equals to 0. So m dot x will get cancelled out. So can I write dm dot by dx that is equals to q dot by lambda dx. I think up to this it's very clear why I'm writing this. Dm dot by dx that is equals to q dot by lambda dx. So from previous expression, can I calculate this dm dot by dx? We can write from here that dm dot by dx that is equals to, this is our formula of dm dot by dx. So we can write here. So that is rho L minus rho B by mu L into G W, and that was equals to delta square and d del by dx that is equals to q dot by lambda q dot by lambda dx, right? Now next what we can do is that dx and dx will get cancelled out. So we can write here rho L minus rho B by mu L GW del Q. Uh, I will be writing a fast because time is very less, so we'll have to complete this in very few time. D del that is equals to Q dot by lambda, right? So next is we can write, since already from the Nusselt theory we have assumed that the heat transfer in the liquid condensate will take place by the conduction only. So we can write that is Q dot C that is equals to K of liquid, because that is getting condensed heat transfer coefficient, thermal conductivity of liquid, minus T saturation minus T of that is surface upon delta x, and this is area is W dx. Why I am writing here? Try to understand one thing. So this distance is our dx. So heat transfer will be taking place from this direction to this direction. So the temperature difference between these two layers is that is delta T that is equal to T saturation minus T set. Okay, and this, sorry, try to understand this thing. The profile is like that, right? If this is delta, okay, so here again I am trying to make this, if this is delta minus y, right? So it will be getting transferred from this to this. So here this will be T surface, here this is a T saturation, right? And if I'm assuming the condensate having a thermal conductivity is KL, and area of this particular plate will be what? W into dx. Why? Here it is W and here it is dx. So the cross-sectional area will be like that. The cross-sectional area that is W and this one is dx, right? So that's why I'm writing W into dx by conduction only, heat transfer by conduction. So q dash we can write that is equals to rho L into, uh, from the previous year we can calculate this value of q dot. Q dot is equals to, it will get multiplied here, right? So we can write here like that. Yeah, rho L into rho L minus rho V upon mu L GW, and that is del square d del, right? That is equals to KL, that is T saturation minus Ts by del, and that is W dx, right? So this W and this W will get cancelled out. Del is function of x, right? Yeah. So we can write rho L minus rho B upon mu L G, and that is equals to del Q d del, right? Del Q d del, that is equals to KL T set minus Ts, and that is dx. So it will be 0 to L, because the whole plate length here you can see this is L, and 0 to delta I am assuming, right? So can I write here that is rho L minus rho V by mu L into G, that is del 4 by 4, that is equals to KL T saturation minus T set minus Ts, and that is equals to L, right? Or at a particular location if you want to assume, right? So can I write here, we'll have to, if we want to calculate that is delta 4, delta, right? Del. So that is equals to, can I write that is del 4, that is equals to KL T set minus Ts into L into mu L into 4 divided by uh, rho L into rho L minus rho V into Z. And here I forgot to write one very important parameter. So that is lambda. That is lambda. So G lambda. Right. So this is the formula of delta 4. So next we can write, just one second, we can copy this. But it won't get copied. So yeah. So directly I can write that is delta 4, that is equals to KL set, that is K of liquid T set minus Ts, and 4 mu L 4 KL mu L multiplied with L, that is divided by rho L, rho L minus rho V into G lambda. And we wish to calculate the value of this only delta. So so mm, it in the right hand side it will come as the power of 1 by 4, right? So this is our delta x. So that is function of k 4 KL T set minus Ts mu L multiplied with L, or here if it want to calculate the function of at a particular location of L, so that is x rho L minus rho V G lambda whole to the power 1 by 4. So from here we'll get some correlation that is very important, and that you'll have to remember for the exam point of view, that is equals to delta is directly proportional to T saturation minus T surface to the power 1 by 4. Delta x is directly proportional to viscosity of liquid. Delta x is inversely proportional to latent heat of vaporization. Okay, and to the power 1 by 4 to the power 1 by 4, and delta x is directly proportional to x to the power 1 by 4. That's a very important correlation that we'll have to understand. So delta x is very important. So that is directly proportional to x to the power 1 by 4. Now, one more important thing is that we can calculate the heat transfer coefficient Hx, that is equals to KL by delta x. Hx is equals to KL by delta x. So we can write Hx, that is equals to KL divided by the value of delta L we have already calculated over here, that is 4 KL T set minus Ts into mu L into x upon rho L into rho L minus rho B into g lambda and whole to the power that is equals to 1 by 4. So you can see it like that. That is equals to rho L into rho L minus rho V into g lambda and that will be equals to kq and upon 4 t set minus ts into mu L into x whole to the power 1 by 4. So here you can see hx is directly proportional to 1 upon x to the power 1 by 4. It's very important. Hx is then inversely proportional to x to the power 1 upon 4. So if you want to calculate h bar, that is average heat transfer coefficient, that is equals to 1 by L 0 to L hx dx. So that is equals to 1 by L 0 to L. Hx is directly proportional to 1 by 4. So can I write h x to the power 1 by 4 dx? So that is equals to 1 by L and x to the power minus 1 by 4 plus 1, that is equals to x to the power 3 by 4 by 3 by 4. So that is equals to 4 by 3 x to the power 3 by 4. So that is equals to 4 by 3 and L to the power 1 by 4, right? So from here we have got the very important relation h bar, that is equals to uh, 3 by 4 at hx is equals to L. Average heat transfer coefficient, average heat transfer coefficient, that is equals to 3 by 4 multiplied with heat transfer coefficient at hx is equals to L. Okay, that is very important formula that we can get from this correlation. So here we have got that hx is inversely proportional to 1 upon x to the power 1 by 4 and delta x was directly proportional to x to the power 1 by 4. So these two correlation is very important. So I hope up to this, the concept of this condensation, heat transfer coefficient, and calculation of the boundary layer thickness in the condensate layer is clear to all of you. Okay, thank you.